to True Projects. In this video, we are going to explain about the project, which is Adaptive Voting Mechanism with Artificial Butterfly Algorithm-based Feature Selection for IDS in MNet. Introduction of the project. In the dynamic landscape of computer science, the project focused on mobile ad hoc networks and the challenges posed by network security threats within framework. MNet serves as a vital conduit for communication where mobile nodes rely on intermediary nodes to access network resources, leading to intricate security concerns. MNet's inherent characteristics such as nodes acting as routers and the dynamic nature of network topology introduces complexities. Security risks are amplified by potential malicious nodes seeking to compromise network infrastructure, necessitating innovative approaches for intrusion detection and prevention. Recognizing the limitations of traditional security tools, the project leverages machine learning techniques to bolster intrusion detection capabilities. ML's ability to swiftly process and analyze data is harnessed to enhance detection rates and adapt to evolving network threats, providing a proactive stance against adversarial activities. The project integrates a diverse set of machine learning algorithms including decision trees, XGBoost, random forest, support vector machine, logistic regression, MLP classifier, and boosting regression tree. This ensemble approach aims to harness the strengths of individual algorithms, fostering a comprehensive and robust intrusion detection system. Objective of the project. The objective is to develop an adaptive voting mechanism incorporating artificial butterfly algorithm for feature selection in intrusion detection systems, tailored for mobile ad hoc networks. The goal is to address the challenges of network security in MNet by improving the accuracy of IDS, enabling effective detection and prediction of the behavior of hostile nodes within these dynamic and decentralized communication networks. The aim is to utilize the NSL-KDD dataset as the input data, applying pre-processing techniques such as SMOD and set-score normalization. This process is intended to remove irrelevant features and normalize the data, enhancing the overall efficiency of intrusion detection system. The focus is on leveraging the artificial butterfly algorithm to intelligently select optimal features for IDS, contributing to an enhancement in the system's performance and its ability to detect network intrusions effectively. The objective is to integrate ensemble classifiers including multi-layer perceptron and boosted regression trees alongside an adaptive voting mechanism. This ensemble approach aims to dynamically select the best classifier, further improving the accuracy of intrusion detection in MNets. The overarching goal is to achieve higher accuracy in intrusion detection through the implementation of the proposed ensemble model by combining feature optimization, pre-processing techniques, and adaptive voting. The project aims to create a robust and efficient solution for securing MNets against potential intrusions. To implement this project, we need software and hardware requirements. Coming to hardware requirements, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. To implement this project, we have designed various steps in the flow of work. So the first step is importing the packages. In this step, essential software libraries are brought into the project to provide functionality and tools which are necessary for subsequent data exploration, processing, and model building. We have imported NumPy for numerical operations, Pandas for data manipulation, Seaborn and Matplotlib for visualization, sklearn for machine learning, Flask and SQLite for web development. Exploring the dataset using NSL-KDD dataset. This module involves delving into the NSL-KDD dataset, emphasizing that the data has undergone prior processing to ensure it meets the project's specific requirements. Data processing. Here we have two substeps. Coming to first substep, which is converting data into Pandas data frame. In this step, the dataset is converted into Pandas data frame, which is widely used data structure in Python for efficient data manipulation and analysis. Dropping unwanted columns. Unnecessary columns are removed during this data processing phase, streamlining the dataset for improved efficiency and relevance. Visualization using Seaborn and Matplotlib. This module involves utilizing Seaborn and Matplotlib, which are two powerful data visualization libraries, to create informative graphical representations that aid in understanding patterns and trends within the dataset. Label encoding using label encoder. The label encoder is applied in this step to convert categorical labels into numerical values, which is a crucial pre-processing step for machine learning models that require numerical input. Z-score normalization. Z-score normalization is performed to standardize the features, ensuring a consistent scale of numerical variables and avoiding potential bias in the model. Mode oversampling. The synthetic minority oversampling technique, which is mode, is applied to balance a class distribution by oversampling the minority class, mitigating potential bias that might arise from the imbalanced data. Feature selection using Artificial Butterfly Optimizer. Artificial Butterfly Optimizer is employed to select relevant features from the dataset. Optimizing the model's performance by focusing on the most influential variables is an optimization algorithm that is used for feature selection in various applications, including intrusion detection systems in mobile ad hoc networks. The algorithm is inspired by locating strategies of butterflies, particularly their behavior in finding optimal positions. It utilizes different flying modes such as sunspot flying mode, canopy flight mode, and free flight mode to mimic the behavior of butterflies. It incorporates features like male butterflies traveling towards sunspot, relocation to neighbor sunspot, and competition among butterflies for best position. The next module is building the model. In this step, we build various machine learning models. The next step is training and building the model. In this critical step, the machine learning model is trained using the processed and optimized dataset, laying the foundation for accurate predictions based on the chosen algorithm. As an extension, we have implemented an ensemble method to enhance the accuracy of the intrusion detection through the combination of multiple machine learning models. Additionally, a user-friendly interface, a front end, has been developed using Flash framework incorporating user authentication for secure testing and interaction. These extensions aim to improve both predictive capabilities of the system and the practicality usability for end users. Flash framework with SQL for sign up and sign in. The Flash framework is integrated with the SQLite to create a robust authentication system allowing users to sign up and sign in securely, enhance the overall reliability of the application. User gives input as feature values. User input their feature values, providing the necessary data for the model to make predictions. The next step is the given input is pre-processed for prediction. The user provided input undergoes pre-processing step to ensure that it aligns with the format expected by the trained model for accurate predictions. Trained model is used for prediction. The previously trained machine learning models are applied to the pre-processing user input to generate predictions based on the learned patterns. Final outcome is displayed through front end. The predicted outcome is presented to the user through the front end of the application, providing a user-friendly interface for interpreting the model's results. Algorithms which are used in this project are decision tree. Decision tree is a non-linear predictive model that partitions the data into subsets based on values of the input features. It makes decisions by traversing the tree from root to a leaf node, where each internal node represents a decision based on a feature and each leaf node represents the output model. Decision trees are advantageous for their interpretability, ability to handle both numerical and categorical data, and suitability for complex decision boundaries. XGBoost. It is an optimized and scalable implementation of gradient boosting. It builds a series of weak learners, typically decision trees, sequentially, with each tree correcting errors made by the previous ones. XGBoost is known for its efficiency, speed, and regularization techniques, making it robust against overfitting. It is chosen in this project for its exceptional predictive performance and the capability to handle large high-dimensional datasets effectively. Random forest. It is an ensemble learning method that constructs a multitude of decision trees during training. It aggregates the predictions of individual trees, bagging to provide a more accurate and robust overall prediction. Random forest excels in handling noisy or unstructured data, reducing overfitting and providing variable importance measures. In this project, random forest is selected for its ability to deal with diverse, potential, complex intrusion detection scenarios. SVM, which is support vector machine. It is a supervised learning algorithm used for classification and regression tasks. It seeks to find the hyperplane that best separates different classes in high-dimensional space. SVM is effective in scenarios where the data is not linearly separable by transforming it into a higher dimensional space. In this project, SVM is employed for its versatility in handling both linear and non-linear data, making it suitable for intrusion detection tasks with complex decision boundaries. Logistic regression. Despite of its name, logistic regression is a classification algorithm that models the probability of an instance belonging to a particular class. It uses the logistic function to map predictions to probability, and it is well suited for binary classification tasks. Logistic regression is chosen for this project due to its simplicity, interpretability, and effectiveness in scenarios where the relationship between features and the target is approximately linear. The last algorithm is MLP classifier. MLP classifier is a type of neural network composed of multiple layers of nodes that can learn complex patterns and relationships in the data. It uses backpropagation to adjust the weights of connection between nodes during the training. MLP is suitable for tasks where non-linearities and intricate feature interactions plays a crucial role. In this project, MLP is employed for its ability to capture complex relationships and intrusion detection scenarios. Boosting regression tree. Boosting regression tree is an ensemble learning technique that builds a series of decision trees sequentially. Each tree corrects the errors made by the previous ones, ultimately improving the overall predictive accuracy. Boosting is chosen in this project to enhance the model performance by combining the strengths of individual trees, providing a more nuanced understanding of the complex patterns associated with the network security sets. We have evaluated this project using different evaluation metrics, which are accuracy, precision, recall, and F1 score. Here we have accuracy comparison graph. On x-axis we have accuracy score for each algorithm, and on y-axis we have algorithm means. Accuracy is the ratio of correctly predicted instances to the total instances in the dataset. In the context of intrusion detection, accuracy represents the overall correctness of the model in classifying both normal and intrusive instances. This is the precision score comparison graph. Precision is the ratio of correctly predicted positive observations to the total predicted positives. In the context of this project, it measures the accuracy of model in correctly identifying intrusive instances among all instances predicted as intrusive. This is the recall comparison graph. Recall is also known as sensitive or true positive rate. It is the ratio of correctly predicted positive observations to the total actual positives. In the context of this project, recall measures the ability of the model to correctly identify all instances of the intrusion. This is the F1 score comparison graph. F1 score is the weighted average of precision and recall. It provides a balance between precision and recall, considering both false positives and false negatives. In the context of this project, F1 score assesses the overall accuracy of the model in detecting intrusions while considering both types of errors. To execute the project, first we need to open the code folder which contains source code files. So this is the code folder of the project. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is the app.py file. This file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. This is the KDD train data on which we will be training the algorithms. This is the sign-up file. This file is the database file used to store the user information. This is the notebook.ipynb file. This is the Jupyter Notebook file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. Now to execute the project, we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. Here we can see that current directory is changed to the code folder's path. Here we need to type python space app.py and click on enter. This command will compile the app.py file and will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flash framework will host the application locally at the default address, which is the localhost and the port. This is the localhost and this is the port, unless configured differently. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. Now we need to open any web browser, so I prefer Google Chrome. I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project which is displayed in the browser, and this web page is built by using the Flask framework. Here we can see a sign up link. First we need to click on it and enter all the sign up details if we are signing up. I have already signed up and I have an account in it, so we'll directly click on sign in. Here we need to provide our credentials, which are the username and the password. So I'm giving my username and the password, and now we need to click on sign in. We have signed in successfully. So here we can see the parameters which are need to be entered. So based on the given parameters, the system will predict whether attack is detected or not. If the attack is detected, it will detect which type of attack it is. Now we will understand all these parameters. The first one is protocol type. It is a type of communication protocol used in the network such as TCP or UDP. The next one is service, which is specific network service or application being used like HTTP, FTP or SSH. The next one is SRC bytes, which is source bytes. It is the number of bytes sent by the source in the network connection. The next one is DST bytes, which is destination bytes. It is the number of bytes received by the destination in a network connection. The next one is wrong fragment. It indicates whether there is an incorrect fragment in a network connection. Coming to the next one, which is number of failed login. It is the number of failed login attempts. The next one is number of compromised nodes. It is the number of compromised nodes or systems in the network. The next one is root shell. It indicates whether there is a root shell present or not. The next one is numroot, which is number of root access instances. It is the number of times the root user is accessed or involved. The next one is number of file creations. It is the number of file creations in the network. The next one is guest login. It indicates whether the login is a guest or not. Next one is SRV count, which is service count. It is the count of services used in the network. The next one is error rate, which is server error rate. It is the rate of connections that had SYN errors. The next one is SRV's error rate, which is service server error rate. It is the rate of service connections that had SYN errors. The next one is DSD host SRV rate, SRV count, which is destination host service count. It is the count of destination host services. The next one is destination host same SRV rate. It is the rate of connections to the same destination host service. The next one is destination host different service rate. It is the rate of connections to different destination host services. The next one is destination host same source port rate. It is the rate of connections from the same source port to the same destination port. The last one is destination host server error rate. It is the rate of connections that had SYN errors to the destination host. Now we will enter all these parameters. So the protocol type is 1, service is 53, source bytes are 3401, destination bytes are 327, wrong fragment is 0, number of failed logins are 0, compromised are also 0, root shell is 0, numroot is also 0, number of file creations are 0, and in-guest login is 0. Service count is 1. Server error rate is 0. Server's error rate is 0. Destination host service count is 140. Destination host same SRV rate is 0.55. Destination host different service rate is 0.03. Destination host same SRC port is 0. Destination host server rate is 0. Now we will click on predict. So based on the given input, it is predicted as no attack detected and it is normal. Now we will enter other parameters and see what will be predicted. I entered all the required parameters. Now we will click on predict. So it is predicted as attack is detected and the attack type is probe. Now we will enter other parameters. Here I have entered all the parameters. Now we will click on predict. Based on the given input, it is predicted as there is an attack detected and the attack type is DDoS. Now we will enter all these parameters again. I have entered all the parameters. Now we will click on predict. So based on the given input, it is predicted as attack detected and the attack type is R2L. In this way, if we enter all the parameters, then the system will predict which type of attack it is. Now we will sign out. Conclusion of the project. The project successfully introduced an adaptive voting mechanism integrating the sophisticated artificial butterfly algorithm for feature selection. This innovation enhances the agility and responsiveness of intrusion detection systems in mobile ad hoc networks, addressing the challenges of dynamic network environments. Through the implementation of ensemble classifiers including multi-layer perceptron and boosted regression trees coupled with adaptive voting, the project significantly improved the accuracy of intrusion detection. This achievement is particularly notable in predicting and mitigating the behavior of hostile nodes, bolstering network security in MNETs. Utilizing the NSL KDD dataset, the project applied effective pre-processing techniques including SMOTE and Z-score normalization. This approach successfully removed irrelevant features and normalized data, enhancing the efficiency of intrusion detection system for optimal performance. The project's utilization of artificial butterfly algorithm for feature selection showcased a sophisticated approach by intelligently selecting optimal features. The system demonstrated enhanced performance, contributing to a more effective and streamlined detection of network intrusions. The project's ensemble model, combining feature optimization, pre-processing, and adaptive voting, presents a holistic and robust solution for securing MNETs against potential intrusions. The achieved higher accuracy underscores the project's success in advancing intrusion detection capabilities with the unique context of mobile and ad hoc networks.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.